Okay, our session is being recorded. We are starting week 3 of Data640. I hope you've spent the last 2 weeks wisely, becoming a little bit familiar with SAS Enterprise Miner, because now we're going to start, especially next week, we'll start getting into the heavy lifting, so to speak, of understanding the primary tools and understanding how to tweak SAS Enterprise Miner to help build models. So we're going to have 2 weeks on decision trees, 2 weeks on regression, 2 weeks on neural nets. Okay, when you come into the room, probably best if you mute yourself so that way we won't get any feedback. I'll try the best I can. Okay, so this is really the last week before we get into the details of how those techniques work and how to use them in SAS. But I'm sure some of you are already experimenting with some of those things. So next week, again, will be the first week where we explain in detail what's going on inside a decision tree, followed by a week of, okay, let's look at how SAS builds decision trees and some of the options, followed by a week of what's going on inside regression models, and so forth. So the flow picks up pretty good from here on, and then, of course, you'll have assignments due. But this is a week always... I won't say frustrates or overwhelms me. There's so much that you could do to talk about model enhancement and evaluation. You know, if you've read a lot of the studies, you know that the advertised percentages are that you spend about 60 to 80% of the time getting your data ready for the model, and about 20% of the time building and implementing the model. And that might not be too far off. Building the models is the fun part. Tweaking the data, getting it ready, I think you gain an appreciation for that once you start doing it and once you start realizing how important it is to get the data in the right shape to build the models. And so we're going to say a little bit about that tonight, including a little bit of a review of evaluation of models. And then, as I said, next week we jump in full bore. So I've got my usual set of slides. But I'll point out some other things where you can get information as we go. So here's the agenda. I want to talk a little bit about general problems with predictive models, and then we'll get into data prep and transforming features. These two areas could occupy an entire course in and of themselves. You could certainly spend an awful lot of time, and should spend a lot of time, getting your data into the right condition. Even when you go through that, SAS Enterprise, getting started with SAS Enterprise Miner 13.1 walkthrough, which I hope you're doing, you'll see they spend some time transforming and preparing the data and transforming features and then selecting features. So we have to prepare the data, transform some of the variables. When I say features or variables, I mean really the same thing, the predictors, the inputs, if you will, to predict the output. And then we'll say a little bit about accuracy measures and get into the usual things here, okay? All right, nice chart. It's from an article, in fact, an article by Sarma. This gentleman's been with SAS for some time because this is from 2008. I think the problems he outlined in the article are still valid. Too many inputs. What happens when you have thousands of possible inputs? Well, think of the various combinations of inputs you could pick from that. To build your models, and so you're going to need some help winnowing that down. What about unary inputs, where all the inputs have just one value? Well, you can get rid of those pretty quick. How about extremely skewed or near unary inputs? You can see again some tips there. Use stat, explore, multiplot to identify those, and maybe set them to reject. Again, a lot of this is trial and error, experimenting, trying things, building multiple models, looking at the accuracy measures, seeing if you're getting better answers. Moderately skewed distributions, too many values. You know, when you have a discrete variable with too many values, that can cause a problem. A moderate number of missing values. You know, when a variable is missing some values for some of the cases, how many is too many to where you throw that out? The answer is no one's quite sure. And many inputs that don't have information value or relevance, okay? So these were problems that have been around for some time. You can see this again from the 2008 article. I would say these are the same problems, but we have a lot more help now in dealing with some of these issues. So let's talk about it. This is from a real good book, Dean Abbott just published this book a couple months ago, Applied Predictive Analytics Principles and Techniques for the Professional Data Analyst. And Dean Abbott is one of the giants. You've seen other articles referred to by him that I've referred to in some of the readings and supplementary areas. He's really quite good. His website is terrific. He writes a lot of articles. He knows a lot. He's a consultant by nature. So he really is into this business. And he talks about a data audit, the things you want to look for, which ties directly pretty much into the previous slide. You want to look for missing values, strange minimum or maximum values, strange means or medians. Are there large skewness in distributions? High cardinality categorical variables, meaning categorical variables that have lots of different values they can take on. Categorical variables, large number of single values. Variables highly correlated with each other. These are things you might want to look for as a starting point, because somewhere along the line you got to get started with your data set and try to get it into the shape you need it in order to build a predictive model. So this is what he calls a data audit, which I think is a good term. So I want to talk about some of these things. Variable cleaning. The easiest and most obvious thing to do is remove errors. If you have instances in the data set. Now remember, for the most part, at least initially in this course, we deal with relatively modest-sized data sets. In fact, relatively small-sized data sets. But sooner or later, even in this course, I will strongly encourage you to try to find a real data set and start using that. Now, real data sets can have lots of errors. Some of the pre-canned data sets that come with the course, many of the data sets at UCI, which has a lot of good data sets to practice with, have very few, if any, errors in them. But real-world data comes replete with errors. So the first and obvious and easiest thing to do is find those errors, whether it be typos, misspellings, whatever, and sort of fix them. Either remove the errors, correct the errors, or eliminate the cases. Then the next thing you might want to do is look for outliers. Outliers can come from several sources. Incorrect coding mistakes. You want to fix those, remove them. Sometimes you have to transform outliers. Sometimes you have to bin the data, meaning take a continuous variable and put it into discrete chunks. Most of the models work better with binned variables. Separate the outliers, develop a separate model. This is one not too many people think of initially, but it's one you might want to consider. Maybe you build a model for all the ones that were within 2 standard deviations, 3 standard deviations, whatever you happen to choose. And maybe you take all the ones that are more than 3 standard deviations out, and you build a separate model. You might find some very good results. You know, if you're just dealing with a model that deals just with the outliers, another thing to consider. And then the final suggestion, or consideration at least, something to consider, is you just keep the outliers because they are meaningful. They mean something. All of the data cleaning, data preparation, data auditing requires you to have a thorough understanding of your data set. And that, unfortunately, is a little difficult to do in a classroom environment. In the real world, of course, you'd want to bring in the functional people who knew a lot about the data set, and you'd want to include them and have them help you figure out what's a real outlier, what's a bogus outlier, what's a typo, and so forth. But, you know, when we're dealing with these in the classroom, you have to use sort of some judgment and do what you can, especially if you get a data set that has outliers. So interesting. That's kind of the easier places to start. So the missing values, again, what are you going to do with missing values? Well, here are the options with missing values. Remove the records that have missing values. You say, oh, I've got 25,000 records, 100,000 records, 200,000 records, 1 million records, whatever. I'm just going to get rid of all the cases, the records, the rows that have missing values. Well, that's fine, except, you know, if you have many variables, 3,700 variables was the number given earlier. If you had 1,000 or 2,000 variables, the odds are almost every row could likely have a missing value or 2. It's a lot of information to collect. And so if you start getting rid of rows that have any missing values, you may end up shrinking your data set down to a very small number. So instead of removing rows or records, how about removing columns, variables that have missing values? Now you're eliminating some of the key possible predictors, and that may not leave you with the right kind to result in a good model. So a better approach, one that we used a lot last semester, and I would recommend this semester, is probably some kind of imputation. There is an impute node in SAS Enterprise Minor. We'll do a little bit of that. We'll get into the regression more than the decision tree. Just a sidebar, decision trees don't have trouble with missing values. There's a whole bunch of reasons for going with decision trees first. They're the most popular technique. They're the easiest to understand. They're very forgiving of missing values. You don't have to select the variables. They pick them for you. We'll talk about how they do that next week. So there's a lot of good reasons there. But when you get to regression and neural networks, you got a problem with the missing values and outliers and things like that. So we do something called imputation. We impute a value. And you have a lot of choices there. You could say give all the missing variables a value of 6 or 0 or something. You could use the mean value, substitute that. You could use a distribution and select from that. Formulate a distribution of the values that are there and pick from that in accordance with the probabilities in the distribution. You could pick randomly from a distribution. You could use some sort of a model. You can actually build models such as decision trees to sort of where the target is the missing values, and use some of the other variables to predict what should have gone into the missing. So the target, the output, becomes the missing values. Pretty interesting approaches. Okay, the next thing we need to think about is not just taking care of missing values, but transforming some of the variables. Sometimes you have a scale problem. Something's in inches and something else is in tens of miles. Causes problems, especially for clustering, but oftentimes for other things too, which is why we oftentimes normalize or get things converted. We'll do a lot of transforming. There is, of course, a transform node that you can use in SAS Enterprise Minor, which gives you lots of options. You can convert variables to more linear relationships. Linear relationships are a lot easier to understand than nonlinear. You want to transform variables often to reduce skewness. Skewness, a measure of how dispersed the data are and how unlike a normal distribution they are, so to speak. And skewness, especially positive skewness, causes problems, especially again with regression and neural networks. So we'll be doing some of that. Some key transformations from a different book. They suggest, again, same kinds of things for missing values. Leave the missing values as they are, which fine for decision trees, but not regression and neural nets. This is a good SAS video, a YouTube video on imputing missing values. You might want to watch that if you haven't already. Standardize numeric values. That's what we already said. Convert them to a z-score so they're normalized. Turn numeric variables into percentiles. That's one way of spreading out the skewness. Turn counts into rates, okay, instead of for occurrences that occur over time. It needs to be a rate per hour or rate per day rather than a pure count. Balance out different tenures, leave missing cases as is. Replace categorical variables with numerical ones. Linear regression, neural networks prefer numbers, not categories. So replace numeric variables with categorical ones. Sometimes we go one way, sometimes we go the other, and you'll experiment with these as we get into building the models. These were some illustrations, again, from that new Abbott book as to what kinds of transformations you might want to use. If your distribution looks like this, that's probably, according to the experts, pretty close. It's not too much skewed from a normal distribution. If it looks like this, you have some kind of skew. How about transforming it with a log 10? If it looks like this, maybe you bin it. In other words, put some of these little ones together with some of the bigger bars so that you get a smoother distribution. If you have a bimodal distribution, perhaps binning it into 2 bins or 4 bins. If you have a negative skew, consider a power transform. Now, this is going to sound like, gee, I can't remember all this. And the answer is you really don't have to remember all this. This is sort of background material. You'll have lots of options in SAS that are semi-automated, but this is important to have the answer to the question, why are you doing this? Somebody's going to ask you. When you say, I had to reduce skewness in the distributions, why? Well, because the models don't work well, and here's what I did. Consider dummy variables for this kind of a distribution. Positive skew, log transform works well for positive skew. A spike in the distribution, maybe you want a dummy indicator of the spike. And then a classic positive view again, log transform. Now, here's a screenshot from one of the models I did, and you see lots of distributions here, right? Now, there's no reason not to just try to transform all of them, because if they don't need transforming, you know, this is again, after studying the previous charts and saying, gee, I got to write some notes down, I got to try to remember this and that. The bottom line is that the software is so powerful that oftentimes you just say, transform all of them. And you tell it to use, well, the one we used a lot last semester was max normal, which basically tries multiple different transformations and picks the one that most comes closest to making the skewed distribution the most normal. Wow, that's kind of nice. As you can see, there's some skewedness here in most of these distributions. So that one. Probably this one is okay, SAS scores, but just about all these others are skewed somehow. And so when you go in and look at this, and by the way, I did a little walkthrough that I'll post tonight where I got this. I did this right from the, you don't even have to build a model to take a look at all these distributions like this. You can use Explore mode. And so you see, looking at your distributions of the variables that you could use in your model, you may want to transform some of those to reduce the skewness. That's pretty easy. Now, feature transformations. This thing, as I said, max normal is pretty impressive. Max normal is one of the options in SAS, Enterprise Minor. It chooses the transformation that yields sample quantiles closest to the theoretical quantiles of a normal distribution. That's pretty neat. So it does it tries many transformations, okay? Log x, square root x, e to the x, x to 1/4, x squared, x fourth. Tries that and compares it, and then the one that gives you the closest to a normal distribution is the one it will pick. And it can pick different transformations, different ones of these powers for different variables. It's not like they're going to pick one of these and do it to all of them. It'll pick whichever one is appropriate. So SAS Enterprise Minor uses these transformations that are skewed or have a nonlinear relationship between the input and target. Log 10 is probably the most popular, but not always. This is covered for you in Sarma, how he used this in his little discussion in Chapter 2, pages 95 to 99, Chapter 3, 153 to 159. So if you've been reading Sarma, and that can be heavy reading at times, you want to go through that very slowly. You can't read Sarma like you do a novel. You have to go through and try to understand what he's talking about and what his references are, but it makes a lot of sense if you go through it bit by bit. Again, it's a lot to digest, but it's very, very good. Very good. And if you do any of the exercises, I think I have the answers from Dr. Sarma for most of them. So if you want to compare some of the exercises. There's some minor twerks because, again, we're using a slightly newer version with slightly different data sets, but pretty close. Okay. Now, let's talk about features a little bit more. If you transform them, that's great. So now you got features that are less skewed. You've gotten rid of your missing variables. You've gotten rid of other things. Are you done? Are you ready to go? No. No. You still have to select which features you're going to use. Transforming them gets them into a better shape for use, but it doesn't tell you which ones you want to use. So we have to sort of fall back on this feature parsimony general rule, which says the fewer the features, the better, for lots of reasons. The more inputs you have, the more feature inputs you have, the higher the probability that they will be correlated with each other, and that causes a problem. Okay, those variables are going to get too much weight because they're correlated with each other as well as with the output variable. Sparseness. Sparseness is a problem. If data are underrepresented in a feature, then, it's not going to work well in the models either. Some techniques prefer fewer variables, believe it or not, and can get more accurate models. Neural networks and regression oftentimes work better with fewer variables. When I took a neural networks course these many years ago, we were told that anytime you get above about 7 or 8 variables, you're probably dealing with too many. You run into all kinds of problems in terms of degrees of freedom, in terms of having enough cases, in terms of having the potential solution space well represented, and so forth. And again, too many variables does increase the possibility of overfitting. This is a curse for predictive models, overfitting. You get a great model that fits great on the training set and doesn't generalize well elsewhere, either on the test set or in the real world. Now, one obvious solution is, well, I'll just try combinations of features. Well, that's true, except once you get to where you have a number of possible features, it doesn't take long because of the exponential combinations to get to where you'd have to be building millions, tens of millions, hundreds of millions, even more models. With only 50 variables, look at the number of combinations you could build. I don't know what the dimensionality of that is, but already at 30, well, at 20, we're up in the millions, right? 1,048,000. When you get to 30, we're up in way past trillions and so forth. So that's not going to work. So what do we do to pick features? Well, we'll come to that. Again, this is one of the real powerful aspects of using the software SAS Enterprise Miner. So feature parsimony, we want fewer features. A couple of general guidelines. Obviously, only pick features that are highly relevant to the problem. You're not going to try to predict the price of oranges based on someone's shoe size. Look for features that are independent. The best feature set might not be the set of best features. There have been studies showing that features that appear to be very weak individually, when you do their relationship to the dependent variable one at a time, and they look weak, sometimes when you put those in combination, they turn out to make a strong set, which makes it difficult, of course. You'd like that not to be true, but then it'd be easier to build models from it. Avoid the degrees of freedom problem. In other words, every time you add features, you obviously have to add more cases to really keep it even. And of course, the data collection problem is greater if you have more features, because you got to go collect all that data. Now, we collect a lot of data. I'm not sure the data collection problem is as bad as it was, unless some of the features are very expensive, hard to get. Obviously, if you said, I can predict whether your car is going to break down if you take the engine apart and give me all the readings from all the parts in the engine. Well, when you put the engine back together, I'll be able to predict whether it's going to break down. Well, that's pretty difficult. Same thing with medical problems. Somebody says, well, I can predict if you've got bad cancer if I operate and take all these pieces and readings and so forth. No. So sometimes it's difficult to collect the data. So the feature selection is really part science, part art. You want features, obviously, that are available. Can they be measured? Can they be retained? Are they timely? Are they accurate? Are they salient? Are they relevant to the problem? Are they independent? Do they cost too much to collect? Are they volatile? You know, the ultimate ironic outcome of this, of course, was the Netflix prize, where they offered $1 million prize for someone who could improve their movie selection algorithm to present to customers by 10%. They put that on Kaggle. If you haven't visited Kaggle, it's a great place because people put competitions on Kaggle and say, go to it, world, and there's prizes. And after several attempts, many attempts, not several, many attempts, a group finally did come up with an algorithm that met the rules to win the prize. The good news is they got the prize. The bad news is the model was of no use to Netflix because it was so complicated and cumbersome that it could not possibly be operationalized. So another reason to have features that are the minimum set that will give you the accuracy you need, which is not something you can always pull right out in the first model. This is another article, or table rather, from Abbott, talking about some of the feature selection techniques that are used. I mean, chi-square is an obvious one, as are decision trees. Decision trees obviously help you pick the variables because they pick them for you. I mean, one of the tools you can use to pick the variables you want to use in other models, regression and or neural networks, would be to run a decision tree and use the outputs from the decision tree, as those must be the key selector variables to use in the other models. That's one approach. And people tried that last semester, and that worked reasonably well sometimes. Not always. But these are some of the tools you use to sort of pick the variables depending on what kind of variables you have. Now, instead of that, SAS has a very powerful variable selection node. Very powerful variable selection node. If you haven't read this part of SARMA, you need to read it. He goes through all 6 of these cases in great detail, showing you how the variable selection node can be used to help you select and pick the proper variables. Now, that doesn't guarantee that that set won't be outperformed by some other set, but boy, does that give you a leg up. So this variable selection node, you put that in there and run it for with the appropriate settings for depending on what kind of case do you have. Do you have a target that's continuous, inputs that are continuous, numeric meaning? Do you have a target that's continuous where the inputs are categorical and nominal? Do you have a target that's binary and the inputs numeric, and so forth? He walks you through exactly in great detail how the variable selection node can be used for each one of these 6 cases, and it's very powerful. So this is one of the key things you need to do to help you select variables. But as I said, you can also use some of those other tools. You can use the chi-square, you can use associations, you can use decision trees, and you might want to try various options. Again, I keep coming back to that. I know you're getting tired of hearing that, but it's really one of the keys. The heavy lifting, the models are created instantly once you tell it to go. But if you don't have a good set of variables, you're not going to get a good model if the variables aren't related and in the proper format and so forth. So this, again, chapter 3 of the SARMA text is outstanding. My favorite chapter, really. Some usage tips. I mentioned this already. Decision trees can sometimes be used to identify the key features. Regression obviously has its own way. It has forward selection, backward selection, stepwise selection, each of which picks variables differently. And you can set multiple cutoff values, as you can, by the way, as you can with this. When you go through these cases, you can set cutoffs, strictness or unstrictness, as to how many variables you want to allow to be selected. Obviously, if you're less restrictive, you get more variables. You might hit on a better combination, but you increase the number of variables and you make the problem larger and a little more difficult to get sometimes the right convergence. Choose fewer variables, and it doesn't find a good relationship. So there's a happy mix in there. SARMA also talks about using cluster analysis to choose variables. We did not use that last semester. I don't see as much value in that as I do some of the other things. So I'm not saying don't use it. I'm saying, again, if you only have a limited amount of time, this would not be my first choice. But cluster analysis, says all these things are the same, so they might be good to put the variables in. You can try that. I would encourage you to try that. You want to balance the case outcomes for the classification problems, avoid the 99-1 problem. I want to say a word about this. SAS has a way of fixing this problem, so to speak. In the past and with other software, we've had to balance the data set because if you put in 10,000 cases and 9,900 of them are outcome 1 and 100 of them are outcome 0, then the model predicts everything a 1 and it's 99% correct. And we talked about that in Data610, where we're using a much more simplistic tool of prediction. A good tool, but not as powerful. In SAS, you can go in you can do that. You can balance your data set. Say, I'm just going to use 50% of the cases a 1 and 50% of the cases a 0, which is good for building a model. Unfortunately, that's not the real world. If the real world is 95% 1s and 5% 0s, then you have to do an adjustment to your model once you get it. Whereas in SAS, you can do that adjustment right there when you're loading up your data set. When it says prior probabilities, you put in the real probabilities. You only need to do that if you're using a data set that is different than the real world. If you're using a data set that's the same as the real world, you're fine. But if you're using a data set that you've stratified because you wanted more cases of the rare outcomes, then you need to put the prior probabilities in of the real world so that the adjustments are done automatically by the SAS program. We can talk more about that at a different time. So ideally, it'd be nice to have an equal number of outcomes for a classification problem. But again, SAS helps solve some of that. You always have to have a test set and a training set. Now, when I say test set, that could be a validation set. SAS has the ability to have you set up 3 different subsets of your data set. A training set you have to build the model, a test set or a validation set, or both. I'm not sure why you need both, but it says, well, the validation set is only used one time right at the very, very, very end. Even after you've used the training set to build the model, you've used the test set to sort of test and validate the model, then use a validation set one more time. So most of the time, I think 2 sets are really all you need. You can separate the data into a training set and a test set or validation set, one of those 2. So other ways SAS helps with variable selection. In addition to that variable selection node, here you go. In the stat explore node, the enterprise miner calculates variable worth using the Gini split worth statistic. Now we're going to say a lot about that because that's one of the key things used in decision tree building. I will explain that and give an example of that next week. But basically, the higher the Gini worth statistic, the better the variable is for predicting the output, independent of other variables. So this would be the best variable right here as the highest Gini worth. Okay. Now remember, these are comparing just that variable against the output, not combinations. Much harder to do combinations. Here's a plot of the top 20 variables by the chi-square statistic. And again, same thing. The higher the chi-square statistic, the better the variable for predicting the output. But once again, this is looking at them individually. This variable against the output, and so forth. Okay, so if we get a data set, we clean it up, we transform variables, we pick features, we build models, then what do? Well, we're probably going to want to build multiple models, or we may use multiple techniques, or we may build multiple models with a single technique at first. Because when we start with decision trees, that's all we're going to build at first. Then you have to compare the models, don't you? And fortunately, SAS, again, has a nice comparison tool that we'll talk more about in a couple of weeks. But basically, you want to compare them on appropriate measures. And there are a lot of measures out there. Confusion matrix, lift curves, and ROC curves are very common accuracy comparison tools for classification models, which is logistic regression, decision trees, and neural networks. Statistic measures, average, squared error, R-squared, root mean squared error are commonplace terms or statistical measures used for numerical models. Linear regression, again, neural networks, and regression trees, which is a form of decision trees designed for continuous variables, estimation variables. So, estimation targets. So we have lots of things. This is sort of a review. Some of you remember some of these slides from 610. I've added a little bit to them. R squared is the coefficient determination. This is for a numerical model, or estimation we call it sometimes. A measure of how much variation you've captured. Of course, we can show it in 2 dimensions. We can't show it in n dimensions, which almost always you're dealing with. But the concept is the same. This is capturing almost none of the variation. This is capturing about half. This would be capturing all of it. So R squared, the coefficient determination, basically a measure of how much of the variation in the item of interest, the target, you are accounting for by the attributes you've selected. So that's a good measure. But we also use average squared error, Okay, another good one. And root mean squared error. Now, sometimes this depends. You say, well, why do I have so many measures? Depends on what it is relevant to your business case. Suppose I have two models, and let's just say we've tested them on 10 cases, and the first model is off by 1 on every one of the 10 cases. It's either 1 high or 1 low. Okay, so its average squared error is 1, but it's always off by 1. The second model gets 8, or let's say gets 9 out of the 10 exactly right. Now, it's not going to happen, but let's just for illustrative purposes, gets 9 out of 10 exactly right, but it misses the 10th one by 5 units. Well, when you square that and divide, you're going to come up with a higher, you may come up with a higher squared error, average squared error than the first one. Which one is better? Well, what would you rather have? A lot of little misses, but not too bad, but always misses, or a model that is right on the money, but when it misses big. Which one would destroy your company easier? Okay, which one is fraught with more risk, more downside? So you have to think about these things. As you know, or you will soon know, in SAS Enterprise Miner, you can put in cost figures for having misclassifications. You can put in cost figures for false positives or false negatives. And that makes it rather sporty because that says I want to use a different kind of accuracy measure than just overall accuracy. I may want a tool that's much better at not coming up with false positives or false negatives depending on the cost of those items, especially if it's medical and things like that. So there's a lot to think about. Now, I know it's overwhelming at first when you start thinking about all this, but you'll see it flows pretty smoothly. Once you start actually building the models, it flows pretty smoothly. So for the classification or categorical models, where you're predicting something is either 1 or a 0 or an X or a Y or one of several discrete outcomes, we have something called the confusion matrix. You know, if the actual class is an A and the predicted class is an A, that's correct. If the actual class is a no and the predicted is a no, that's correct. So these are true negatives, true positives. These are false negatives, and these are false positives. Okay? So we have to, these are correct and these are incorrect. So the question is, well, do I just want an overall accuracy measure, or do I want to focus on minimizing one of these? I say one. Can't minimize all of them. Okay? So sometimes we use just an overall accuracy measure, which would be the accurate numbers divided by the total. That's your overall accuracy. Okay? Sometimes, however, we prefer something called sensitivity, which is the proportion that are yes and predicted yes. Okay? So it's A over A plus B. Okay? These are the ones that are predicted yes, and the proportion of yeses that are actually predicted yes. Okay? Sometimes we're interested in something called specificity, the proportion that are no and predicted no. And make sure we don't get any no's that aren't right. And again, this was a little example I used in 610 just to run through it again. If you had a 9,990 cases out of 10,000 were zeros, then the model should just predict everything 0 and be 99.9% correct. But that's misleading because it's never going to predict a 1. They would tell you don't mail, let's say you're trying to mail out to customers, don't mail to anybody. Okay? So equal number of cases. This is putting some cost figures in, okay, to give an illustration of that, a very simple problem. Let's say it costs you, okay, if it's a plus and predicted plus minus 1, if it's a plus and predicted minus 100, these are costs. So negative is good, positive is bad, and it's cost. And here, if the actual is a negative and it's predicted positive, 1 and a 0 for negative, negative. If you run through a couple of sample cases, let's say model 1, these are correct, remember, 150 and 250. These are wrong, 60 and 40. The actual class was a plus, and the model said it's a minus. The actual class was a minus, and the model said it was a plus. Here's another model, which has, again, positive, correct numbers, and incorrect numbers. So the overall accuracy, remember, was the ones you got right divided by the total. So here's 150 plus 250 divided by 500. So 400 divided by 500, 80% accuracy. This one is 450 divided by 500, so 90% accuracy. Which model is better? Well, 90% is better than 80%, so this model is better, isn't it? Unless you start folding in the costs. Okay? Start folding in the cost, then we have to take into account these cost figures up here. So this model, 150 times minus 1, that's good news, plus 40 times 100, that's bad news, plus 60 times 1, that's bad news. Remember, these are the ones that got wrong. It cost you 100 to predict a minus when it was a plus, and it cost you 1 to predict a plus when it was a minus. So the cost figure comes out to be 39.10. If you do the same cost calculations over here, the cost comes out to 42.55. So yes, this model was more accurate, 90% versus 80%, but this model had better cost figures. Remember, these are costs, so lower is better. We're doing cost figures in this example. So it doesn't always turn out that the overall accuracy is really the key. Okay? Sometimes we want to use something else. There are other things we can use. We can use something like those cost charts I just showed you, or we can use ROC curves. ROC curves are really neat. They plot sensitivity on the y-axis and 1 minus specificity on the x-axis. So here's where you want to be. You want to be right up here, top left, because you'd like to be 0 false positive rate, and you'd like to be 100% sensitivity. So you'd like to be right up here. So this is the perfect place, okay? If you're over here, you're doing great on sensitivity, but terrible on false positive. If you're down here, you're doing terrible on, well, you're doing terrible on false positive rate. So, you know, this is a random line, and what you find is you can plot ROC curves. Where do they come from? Well, they come from the classification matrix based on having different levels for the threshold for classifying something as a 1 or a 0 or a plus or minus. Let me go back to that chart. Behind the scenes on a classification model are numbers. When something comes out being classified a plus or a minus or a 1 or a 0, there's really a number behind that. And the basic threshold in every software package is 50%. Okay? So if the number comes out 50% or more, you're going to get a plus. If it's 50%, less than 50%, you're going to get a minus. Okay, that's built in, but you can change that. And when you change that, you get these different points because you get different levels of false positive rates and sensitivities. So all of these little dots reflect changing the threshold, and that's how you get the curve. Okay. Where do you want to be? Well, as I said, this is optimal right up here in the top left. So you want to be as close as you can. So if you said, I'm only interested in the most accurate model, or the most accurate threshold, it would be this point. Now, what we really do with ROC curves more often is, and here's how one was built. Again, setting the threshold. This is for diagnosing a tumor of some sort. You know, you can diagnose it with a T4 reading instead of a 50% or 60% or 70%. They did it with the number of the T4 value. You can see that as I change the T4 value to determine what's a hyperthyroid or a euthyroid, the numbers change. Now, you can't improve specificity and sensitivity both. You can improve one or the other. As you see here, the specificity is 9.9, the sensitivity is 5.6. That's not what I want. Well, I can raise the sensitivity, but I lowered my specificity. I can raise my sensitivity even more, but I lower my specificity even more. So the question is, which was more valuable? And that, again, depends on the cost figures. So what we use ROC curves for a lot is comparing multiple models. Suppose you built 5 or 6 models. Here's 1, 2, 3, 4, 5, 6 models. Which of the models in general is best? Well, it's the one that has the steepest slope. In this case, it would be the purple one. So the purple line, for the most part. Okay, the purple line has got more on it. And we also try to measure something called the area under the curve. The perfect one would be 100%. 100% AUC, we call it. That's the area under the curve that's represented here, what percentage it really is. So here we have three models, and we compare their ROC curves. We see that Model 1 has an AUC of 78%. Model 2 has an AUC of about 51%, and the random line, of course, is 50%, basically, because it separates the total curve into two pieces. Now, what's considered a good model? Well, most people say 0.9 to 0.1. If you've captured that much of the area, that's an excellent model. 80 to 90, good. 70 to 80, fair. 60 to 70, poor. 50 to 60, not much. So when you get your ROC curves from multiple models, this is something to look at. And we'd want to have multiple models, and SAS would give you the ROC curves, and you can say, aha, that one looks best. A good accuracy measure. We also have lift charts. Remember what a lift chart is? How much better am I going to do compared to a random guess? That's called the lift. How much improvement does the model give me? So you get lift scores for various portions of your data set. If you recall, we looked at this one little example again in 610. And some of you weren't in 610, so let me run through it. Suppose last year we sent the marketing material to 200,000 leads, and we only got 1,579 of them customers, conversion rate of 0.8%. So now we buy another mailing list of 200,000 leads, and we'd like to know in advance which of the new leads are more likely to buy the product. So we're going to take that list from last year, okay, using the key criteria. Those will be the input variables, and we're going to build a model and compare it. We're going to take 120,000 of the 200,000 and use that as the training set. We're going to take 80,000 and use that as the test set. Okay. So we build a model. The list of leads in the test set was ranked, ordered by score. You know, once we build the model, we run it against the test set, and we get values on how likely the customer is to respond. And we rank them by score. And then we split them into 10 sections, the deciles. So we have 10 deciles. Since these are all historical needs, we know how they actually came out. So let's take a look. Okay, this is our test set, ranked in terms of 8,000 per decile. Okay? And we go say, since this is past data, we go say how many of these people that were ranked by our model as being the best ones in the first decile, the first 8,000, how many of them actually were converted into sales last year? 252. What percentage is that? 3.1%. What is our overall conversion rate last year? 0.8%. 3.1 divided by 0.8 is roughly 4. So we got a lift of 4. So if we only mailed to the first 8,000 people on this year's set, we could expect to get about 252 sales. And this, again, is last year. This is how it turned out last year, and we're assuming the new mailing list is similar in you know, demographics, etc. What if we mail to the next 8,000? We can expect, based on, again, last year's data, 115 conversions, 1.4. 1.4 divided by 0.8 is a lift of 1.8. And of course, the more you go down the deciles, the lower the lift becomes, to where if you mail to all of them, you're going to get exactly what, if you mail to the 80,000, you get exactly what you got last year, 0.8. So that's a lift example. Pretty neat. Pretty neat, especially if you're trying to say, I'm only going to mail to a smaller number this year and save money on the mail. So a lift chart, obviously, again, lift chart, ROC curves look a little bit similar in some ways. How much lift are you getting? And of course, here was that chart we just did. You can mail to the first decile and get about 40% of the sales. All right. So what are we going to do this week? If this isn't overwhelming enough, it overwhelms me just to keep thinking about all of it, because it's so much to absorb. But you'll get used to it as you try these various things. And there's a lot of ways of doing things in SAS Enterprise Miner. There's a lot of ways of doing things. You don't have to use the variable selection model. You don't have to use the max normal transformations. You can try others. In fact, they're not appropriate for all situations. And learning when to use which ones, a lot of that is building models, trying things, experimenting, seeing what you get for results. So what you want to make sure you do is finish the required readings, multimedia viewing, As I said, I built another little short walkthrough to give you a little bit of an idea where you can start viewing some of your data. You want to continue with your SAS Enterprise Miner 13.1. If you haven't gotten through decision trees, you probably want to get through that in the next week. You want to look ahead and start looking at the SAS available data sets. There are a lot of data sets out there. Ideally, you would be using real-world large data sets requiring lots of data cleaning, lots of transformations, lots of variable selections, okay? But to get you started, I think it's better just to go with one of the SAS data sets or one of the UCI data sets that have been used many, many times. They're in reasonably good shape. However, there are a lot of SAS data sets. And when you get to building your models for assignments, you want to have a good, robust data set with lots of variables, lots of cases, and that gives you lots of options to build things. And some of the data sets are, quite honestly, not well suited for predictive models. I'm not going to tell you which ones, but you'll notice when you start going into SAS Studio and looking at the many, many data sets, pulling them in there, looking at the variables, some are there for data visualization, some are there for clustering, which is not a supervised model, or association, which is not a supervised model. Some are better suited because they have a clear-cut target, etc., for building a supervised model. We're going to build supervised models. So you want to start looking at those various data sets and trying to do that. Now, I don't want to discourage anyone from going out and getting a real-world data set. I just want to warn you that they do come with a price to pay, which is what many of the students tried, and not all of them successful last semester. They all said, I want to go get a real-world data set. Well, okay, you get one of the Kaggle data sets, or you go get a data set and put some sources in there from government data sets, etc. In the Leo site, there's some sources that you can go to get data sets on the web. They do come with a price, and the price is usually a lot more time spent getting your data into shape before you can build a model. The payoff is, of course, I have to reward that in terms of effort if you're successful. So the worst case is you pick one of those and you can't build a model at all because you never get to the data cleaned up enough. But the best case is, again, probably for the first assignment or so, maybe even the first two, I would say you might want to stick with a reasonably sized data set from the SAS inventory or from the UCI site because those are in reasonable shape. Not perfect, but reasonable shape. As always, contribute any insights to the discussion area. It's been pretty active so far, and that's been great. A lot of good questions. Not all of them can I answer, but I usually try or find the answer, and I think that's good. I like that. Of course, you can always ask questions by phone. Okay, our hour is about up. Here's our final slide, as always. It says if you have a question you want to ask right now that's you think would help clarify things tonight, go ahead. As always, during the week, if it's a question that you think the answer would benefit all, put that in the Let Me Have Any Questions area. If it's something related only to you, then, of course, a personal email or phone call of emergency is fine. So let me pause there. As I said, this is a lot to absorb. Go through SARMA chapters 2 and 3 very carefully. And then, of course, chapter 4, we'll get into that next week because that's really the well, next week we'll talk about decision trees, and almost week 5, between weeks 4 and 5, you'll have to read chapter 4 of SARMA and start building the tree so that by the end of week 5, you can turn in your first assignment. Remember, the assignments are due at the end of the week in which the assignment is due. So the end of week 5 will be the first assignment due. So you got a couple more weeks. And it's a lot to absorb. I told you last week, this is like eating an elephant, one bite at a time, as the old joke goes. If you just learn a little piece, try something, practice it a little bit until you're comfortable with it, then move on to the next piece, I think you'll be fine. So definitely spend a little bit of time reading about transforming variables and selecting variables. And then, of course, we'll get into the decision trees next week. Okay. Nice to have so many people here. Again, there's no reward for attending live or penalty for not, but it's always good to have a group here to keep me honest. So I don't see any questions showing up in the chat window at the moment. So I think I'm going to go ahead and stop the recording. Actually, I'm going to stop the sharing first if I can get this. Stop sharing. Do that first because it might still be. And then I will stop the recording.